All right, this is where we are in Canvas week 2 of rotation. Today we're going to do, I've got a warm up for you here in a second. We're going to do some notes and then we'll do rotation 3 together. We're not going to do the entire document. We're only doing the components that are free response, not the ones that are multiple choice. Any of the multiple choice ones I haven't looked at, I don't want to look at, and I'm not assigning them. You should have enough time to get into the homework. What's listed here, TAW, or anyway, it's the practice problems. I'll let you have time today to get into those. So we should have enough time to get to all of this. That being said, welcome the next person class, and let's go to our warm-up. So take a second to look at the warm-up. Here you've got 4 signs that are hanging. It looks like 2 of them are 50 kilograms, one that's 90 kilograms, one that's 100 kilograms. And we want to rank the magnitude of the torque the signs exert on the point at which the rod is attached to the side of the building. We want to know biggest to littlest. You can put it in the chat if you know it. I'm going to ask for out loud answers as well, but I want to give you a minute or so just to look at it and kind of get those rankings in mind. So take a minute and look at this. All right, I think we've had a minute to at least get an idea of what's going to have the greatest torque. What's going to have the greatest torque? All right, I know my speakers are up. Your mute is on, so unmute and tell me which one of these is creating the greatest amount of torque. Just the greatest. I don't care about the ranking, just the greatest.
B.
B, absolutely correct. Absolutely correct. So here, the theta, the sine of theta is going to be 90 degrees. So the sine of the angle is going to be 1. We're not worried about it. Now we're just, and they all have the same length of rod. So the radius is the same. Now we're just looking at the force, and 100 kilograms is the largest and it's at 90 degrees. So yeah, absolutely B. I think then we can say, okay, well, with that way of thinking, D, that last one, is the more reasonable one. Because again, you're at 90 degrees, you've got the next largest mass compared, the other two are 50 kilograms. So we know B first. Yeah, absolutely. Good job on that. Then it's D, B, D. All right, which one would be next, C or A?
C.
Yeah, it'd be C then A. Now, when we're looking at this, all the other ones that we did, all the problems that we did in the past, the line of action we were drawing horizontally. Well, this one is pulling instead of pushing, like it's pulling it, and it's pulling it kind of from the top. So our line of action that we would draw here would be vertical, and then we would use the 60 or 30 degrees. We wouldn't need the complement of the angle. It may be confusing to some because of how we finished the homework. Remember the fidget spinners, and it was giving us the top angle instead of the lower half going from horizontal, and we were always going back to the horizontal. Here we need to make sure that we're drawing the line, an appropriate line of action, either vertical or horizontal, and we're able to use the angles they've listed. So BDCA should be our order when we scroll through this. Let's see if they got it right. BDCA, yeah.
How do you know when the line of action is vertical versus horizontal?
I would look to see how the system is being affected. Okay. And that's a great question. Knowing how to draw the line of action. In this case, I think I have this set up where I can draw on the screen. Let's look at A. I would say that A, this weight is pulling this way, right? It's not pushing, it's pulling, right? And it's pulling from this top part. It's taking this vertical and it's pulling it down. And so then my line of action is right here. Now, if it was pushing, I would say, okay, well, it depends how I was looking at it. The way that I'm looking at this one, though, is I've got a line of action that could potentially be here, and I've got a line of action that could potentially be here, right? I've got a vertical or a horizontal. So let's look at what action is happening. And here we're pulling it from the top down, right? At that angle, we're pulling it top downwards. So our line of action is coming from the top, and that's why we can use the vertical. I look at the diagram and I evaluate each way, and it usually comes clear when I'm evaluating it in that format. You know, draw it vertical and horizontal, and then say, okay, where is the force being acted on? Here, the force is acting on pulling it from the vertical downwards, the way it's done. Does that sort of make sense?
Yes.
Ish? Okay. All right. That brings us into, okay, we've got through the warm up. We've at least woken up. We had a great weekend. It wasn't a 3-day weekend, but at least the sun is shining this morning. I'm in a classroom with windows, which is unusual for me. Only in 1A do I get a classroom with windows. So that brings us to our notes. So let me zoom this in. All right, we're going to start a little bit easy with the notes, and we're only going to add just a touch. We're going to take what we've already talked about, and we're just going to make slight increases in knowledge. If you looked closely when I showed where we were in Canvas, which I'll flash back over to real quick, see what's next class on Wednesday? We've got a quiz with FRQ. So we want to make sure that we're solidifying our information up to this point, because next class is a quiz with FRQ. After that, we still have rotation with momentum and rotation with energy. And then that finishes the unit, which is really cool because rotation is really hard. But let's get into what we're doing today. All right, let's see where I can click on. There we go. Brings us into our notes. All right, I have this titled as Rotation 3 lecture. We can title it however you want to, but this brings us into Rotation 3, which is the name of our worksheet that we're going to work on today. If we remember from, I don't know, what was it, like Newton's second law? What was Newton's second law? So let's put Newton's second law. And Newton's second law had something to do with forces, didn't it? It was something to the effect of summation of forces equals mass times acceleration. Okay. I'm going to use this equation, but I'm going to rearrange it so that it solves for acceleration. And we can say that acceleration is equal to the summation of forces divided by the mass. Okay. This is no great mystery, right? You guys were here in, I mean, it seems like it was somewhere in the fall that we were talking about Newton's laws and forces and all of that. We went into forces a little bit deeper, and we did Atwoods. Remember Atwoods? Those were you had something on a tabletop and a pulley and something hanging off the side. So if we go back to our thought from our forces unit, let's say that we have an M1. This is our M1 mass. So that's M1. I know my box is really crazy for a Monday. And then we've got a little pulley here. And then we've got, that's the edge of the tabletop. And then there's a line that connects M1. And then let's put M2 down here, M2. Okay, that's messy. Let's see if I can clean that up just a touch. There we go, M2. All right, and then we know that we had tension on both sides, and tension is pulling up on M2 where we've got M2G pulling down on it, and tension is pulling this way on M1. And we said that tension, because this is a single cable, tension is the same throughout. I want to add one more qualifier to that. Okay, we didn't need this qualifier before, but we sort of need it now. In this case of what I've drawn, this round little pulley in the middle, it has no mass for this example. It's not affecting the system. It's not, it has no resistance to rotation. Okay, the fact that it is a single cable and there is no mass in the middle of it, the tension is the same throughout. If that pulley had a mass, which would give it resistance to rotate, the tension wouldn't be the same on both sides. Okay, so I want to just clarify a sentence from the fall where we said, hey, one line, one tension. One line, one tension also meant there was no mass in the middle of that line. And this is a massless pulley, the way that we've set it up from the fall, repeating it now. If we're good with that, that's awesome. So now if we were to look at the acceleration of this system, we would say, okay, well, we said acceleration is equal to the net force divided by the total mass, right? And the total mass in this case, we've got M1 plus M2, kind of brings you back to big freaking object, okay? If remember we would do big freaking object, we'd say, okay, it's M1 plus M2 and it's only being pulled by M2G. I know it's a throwback to the fall, but we can handle it. we're going to use, instead of big freaking object, which was a simplistic way to look at things, we're going to say, okay, the net force divided by total mass. And that's how we're going to define the acceleration, net force divided by total mass. So then let's go one step further and plug in what we have. The net force is m2g. And the total mass then would be m1 plus m2. And even if you took a second to look at it as a big freaking object and said, okay, well, big freaking object would look something like this, m1 plus m2, and the only thing pulling on it is m2g, right? We put it together, we just skipped the big freaking object part because we know, yes, what's going on?
I had a question. So in the summation of forces, wouldn't tension like cancel out? Or shouldn't it be like m2g minus t?
Okay, if we consider it just as a big freaking object, we know that m2g is the only force acting on the big freaking object. If we look at it in terms of today, we can say, well, tension 1 is pulling up, and or if we said that as far as the system's acceleration, tension is not affecting the system. Tension is only affecting internal components of the system. But as a system as a whole, tension is on the inside of the system. And here, this is net force on this is an external net force. This is a net, the net force here, let's identify this. So M2G, this is net outside force. Where tension is an inside force. And then this is going to be total mass. And I'm going to put in parentheses that this is mass and plus effective mass, which doesn't make sense yet, but it will.
All right. So if you were to find the acceleration of just one object in there, then we would include tension.
If we're looking for the acceleration of the system, which includes the acceleration of this, all objects are connected. So they will all have the same acceleration. And the acceleration will be based on the total mass, m1 plus m2. That's your total mass. And you're going to only look at outside forces. And the only outside force here is gravity pulling on m2. So you would have m2g divided by the total mass, and that gives you the system acceleration.
Okay, got it. Thank you.
Not a problem. These are good questions because this is laying the foundation of what we're going to explain today. Okay, this is meant to be kind of a flashback, a reminder, a filling in the blanks, and then we're going to add to it. All right, so if we're satisfied with saying that a system's acceleration is based on net outside force divided by total mass, which is mass plus effective mass, we have to ask ourselves, well, what is the effective mass? I'm glad you asked. Let's look at things. So this was all based on linear. Okay, this is Newton's second law, and this was my linear example, linear. Okay, so what if we have rotation? Well, we know that alpha is equal to the summation of torque divided by rotational inertia. And if we forgot that, that's okay, because we can go back and say, well, remember, torque is equal to I alpha. And I've just rearranged the equation to say that the rotational acceleration is equal to the, let's put the summation sign, the net torque divided by rotational inertia. Okay, now we're going to solve all problems involving linear acceleration by starting at, we're always going to start at and say that alpha is equal to net external force divided by total mass. We're always going to start with that because it's always true. It is always true. But we need to also include rotation and understand that. It's going to work for regular force problems and rotational problems. Just remember that in rotational problems, you also need to identify the effective mass. And I'm going to show you an example for that. Okay, so let's look at an example. If I've got, let's say, let's do this. That's my disk. Pretend like it's a perfect circle, because in my mind, it is a perfect circle. All right, and then here's our radius. And then we've got, there's a string wrapped around this, okay? And the string comes down and is hanging down, and I've got a mass. Let's call the disk M1, and then the mass hanging down as M2. Okay. Now we know the tension of that string coming down, it's pulling down on M1, causing it to want to rotate. We also know that it is pulling up on M2 because that's what's keeping M2 from just falling with M2G, right? We know that gravity pulls down on this, and it has M2G pulling downward. Let's see, mass in this case, the mass 2 in this case will not have acceleration equal to gravity because the disk resists a change in rotation. So the disk is resisting it. And we said for a disk, I equals 1/2 mr squared, if we remember that. Because of mass and the spins, we must look at the effective mass of this disk. Okay, so we want to look at the effective mass. I brought up that term earlier, but I haven't fully defined it for you. The effective mass, if we know that generically speaking, I equals mr squared. So that means mass then would equal what? I over r squared? This is your effective mass. I over r squared is your effective mass. Now, the only force acting on this system is just like on the left side. M2G is the only force acting on this system. I'm going to change colors just slightly so that way as we're going along, we don't get lost in the order of what I wrote things. If we remember, A equals the summation of forces divided by M, that mass includes the effective mass. So then let's use this equation and then write in our information. We would have the summation of forces. Well, the only force acting on the system is M2G. The only force at all is M2G. Now we need to divide by total mass. Okay, well, there's an M2. And then there's also I over r squared. Now, before you ask a question like, well, wait a minute, isn't it 1/2 mr squared? Yeah, give me a second. Don't worry, I'm going to introduce it. It's going to get there. We know for this example, let's do this over here on the right. I divided by r squared. For this example, I is what? What did we say I was for this example? 1/2 mr squared? So 1/2 m1 r squared divided by r squared. The r squares cancel. So that means the effective mass is basically 1/2 m1. So we can come back down and do replace it and say m2g divided by m2 plus 1/2 m1.
Mr. Watley,
Yes.
I got kind of confused when you wrote that second last problem where you crossed out the r squared. Where'd you get that one from?
Okay, see the place where I just boxed in my answer?
Yes.
Okay, look right above that. I'm going to draw an arrow for anybody that's not quite sure. All right, right here, we're saying that the total mass, the total force, external force on this system is simply M2G. That's my top, okay? On the bottom, I'm saying that I've got my mass M2 plus my effective mass, which is calculated as I over r squared, okay? Are we okay with that statement before we move forward? Because we know I equals mr squared. And if that's for our effective mass. I equals mr squared. And I'm going to rearrange that to solve for the effective mass, which would be equal to I over r squared, correct? Okay, so if the effective mass is I over r squared, for this example, what is I? I is 1/2 mr squared. So 1/2 mr squared divided by r squared is the effective mass. That's when I came over here and I solved for this particular problem. I said that I over r squared is what we have as the effective mass. For this problem, what is I? It's 1/2 mr squared. Well, if I have r squared in the top and r squared on the bottom, they cancel. And that left me with 1/2 m1. It's confusing. It absolutely is freaking confusing. But it's leading us to say that the resistance to rotate of m1 is causing the acceleration to be smaller because we're dividing by a larger number. We're not just dividing by m2, we're dividing by m2 plus 1/2 of m1 because it's a disk. It's 1/2 m1 for the effective mass.
Mr. Watley,
Yes.
I'm not sure I understand the part from I over R to like after that.
Not a problem. Let's step it through one more time, okay?
All right.
I'm just changing back to black. We know that I equals mr squared. I don't care what your object is. We know from our formula chart, I equals mr squared. When I rearrange this equation so that I can solve for m, I'm going to say that I divided by r squared equals m. It's a simple rearrangement. I divided by r squared equals m. In our problem, for a disk, I equals 1/2 mr squared, correct?
Right.
So I'm going to take what, for our disk, this is what I equals, this right here, right? So
Correct.
this is an I right here, isn't it? So I can take that I out and I can put in 1/2 mr squared, can't I?
Yeah.
That's what I'm going to do then. And I don't mean this sarcastically. Please don't take it that way. I want to ask a leading question and say, well, that's what I'm going to do. So now I'm going to take this information and I'm going to plug it in down there. I'm going to say 1/2 mr squared divided by r squared equals to the mass. My r squares cancel. So my effective mass, let's do this. The m on the right, this is effective mass. So up here at the top, that's 1/2 m1 r squared divided by r squared. So 1/2 m1 is equal to the effective mass.
So according to this, the mass of like the little pulley thing is larger than the total mass? No, that doesn't make sense. I don't think I understand the mass part here.
That's okay. I think at some point we just move forward and we use it in more examples, okay? I think with example problems, there's an area to learn. What I'm showing you is how do we calculate a resistance to rotate into a mass? Because that resistance to rotate is just like any other mass. If we have a truck, it's harder to push than a car. A bus is harder to push than a car because it's a bigger object, right? It's a bigger mass. It resists acceleration, correct? Well,
Right.
if we have a large disc or a ring or a sphere or any other rotating object, the bigger its mass, the more it's going to resist rotating, which means it's going to have a smaller acceleration. So the way that we handle it in rotation is we call it an effective mass. Okay. And the way that we're able to calculate it here is the effective mass, the way that it's dividing or the way that it's affecting the acceleration is for this problem, it's 1/2 m1, 1/2 times the mass of 1 plus the mass of 2 is being calculated as the total and effective mass together.
Okay, I think I get it. Thank you.
It's okay. I mean, I hate to feel like I'm like browbeating you on it, but it takes just a little bit of, sometimes it takes like writing it down saying, you know, I don't quite believe this, but okay. And then working some problems through. And as you get through the problems, sometimes it just starts to click. And so we need to kind of work through some problems and see, can we get it to that point of click? And just have faith that have faith that the journey is going to bring us to the solution. And we're not going to make a simple definition and say, okay, got it. Now let's go practice a bunch of times. Because if we got it, why do we need to practice? We have it. Let's look at some problems and see how they step us through and see how we can apply this information.
Mr. Watley,
And yes.
there's some other variable for effective mass.
Is that a question or an answer? I'm sorry. I thought you were telling,
No, I'm asking.
is there another variable for effective mass?
Yeah, because it could get confusing with the mass, I feel.
It could get confusing, but we always use M for mass. So we're going to use M for mass. I'm sorry. And
Okay.
it can get confusing. It totally can get confusing. I think that's why when I warned that rotation is the most challenging topic, it's challenging for different people for different reasons. And that's part of the struggle, I guess. Let's try some practice and see how far we get and see what it looks like. I'm bringing up rotation 3. This comes from Canvas. Again, if you open this packet, and I know attentions vary as we go through things, you can see that initially there is 2 pages that has questions that are free response. It's up to you to come up with a solution. Starting on the 3rd page, it goes into multiple choice. We're not doing the multiple choice component. We're only doing the free response component. After that, we've got a homework page that I'm pretty sure Ms. Doyle put together, but we're going to work the majority of this together. It steps us through the problems. That the ABCD really just helps us. Once you get this, now you can do that. Let's work through these problems. Let's reason them through together and see if we can kind of develop our knowledge. Okay. Don't fear asking questions either, but it does take asking questions and having faith that as we go along, it is meaningful information. Let's take a look at this first one. It says a rod of mass M is attached to a horizontal axis and a thread as shown. What's the moment of inertia of the rod about the axis? Okay, I'm just zooming this in so we can see it a little bit better and I have more room to write. Okay, I'm gonna draw this off to the side because when I have drawings, it makes it easier for me. I don't think I need to draw anything until B. So let's just look at this. Let's see, if the pivot point is at the end of a rod, do we remember what our moment of inertia is? Remember, moment of inertia is rotational inertia or rotation. Do we remember what it is for a rod? Yeah, absolutely. So I is equal to 1/3 ml squared. So at least it's starting easier, right? This isn't something that we're having to stress about yet because, hey, let's just start basic. It's a rod, it's rotating on the end. We flipped through our notebook and we found it. I equals 1/3 ml squared. Okay, so now find the tension in the thread of the system if the system remains at rest. Okay, this is where I want to come over and I want to draw a little bit. I feel like when I draw something, I understand it better than looking at a picture that was drawn, even if they're identical. Just, I think the process of drawing it brings out information for myself. Okay, so this is my rod. And I know from the center, since the mass is evenly distributed, as far as I can tell, I know that mg is going to come down from the bottom. So I have mg there. I know that I have a thread, and yeah, they said a thread. Thread's right here, it's pulling upwards. So I have tension from the thread. And if it's just this, the system would rotate or, or it would fall over or something. So at that pivot point, that pivot point is also supplying me a force going up. I'm just gonna call that force applied from the pivot. That's the reason that it's staying up on the left side. Otherwise, it would just fall. This is like the table legs. Remember last class where we said force 1, force 2 from the table legs? It being attached on the left side is like that table leg. There's a force being pushed up from that pivot point. That's why gravity isn't making it fall. And then on the right side, tension is pulling it up. And then we've got the force of gravity from the center because that's where the center of mass is. Okay, I know that, let's see, the tension on the right, I'm gonna change colors a little bit. Let's put the yellow in. All right, the tension on the right, it wants to make this thing rotate that way. And then since my pivot point's on the left, I know that gravity wants to make it rotate that way. Yeah, the yellow sort of shows up. I didn't want it to be intrusive to my drawing, but I at least wanted to kind of isolate a couple of things. It says find the tension in the thread if the system remains at rest. Okay. Okay, so find the tension in the thread if the system remains at rest. All right. The way that we started our problems last class, there was a listing where we sort of kind of followed through, and we started with the summation of forces. Summation of forces in this case is equal to 0 because it's not moving. And that's going to be equal to, we have what? FA plus T minus mg. Would that make sense? We have force applied going up. We have tension going up. We have mg going down. Yeah, that makes sense, right? I say it that way because, when I'm doing it for the first time, I'm looking at it and reasoning it through. And then for torque, our summation of forces, so our summation for torque would equal 0 because it's not rotating. And then here, mg wants it to go counterclockwise. So I could call that negative if I wanted to. So I would say, okay, what if that is negative mg times 1/2 of the length? Because remember, torque is the force times the distance from rotation. And they said the whole length was L. And mg would be located at the halfway point. All right. And then we said that torque wants it to go counterclockwise, which is positive. So we could say plus TL because torque is the force and L is the distance from pivot. I'm going to do one more step here. I just want to show that I'm going to simplify this equation, or at least since I have 0 is equal to negative mg times 1/2 L plus TL, I could add the negative to the other side and say mg times 1/2 L is equal to TL. If I divide both sides by L, wouldn't that solve for T? Sort of, kind of. If I divide both sides by L, T is on that, so my L's cancel. I'd have mg times 1/2, which is the same thing as mg over 2. Okay. Now that we got that far, do we have any questions on where this came from?
Would we do that with the forces equation too, or no?
Find the tension in the thread if the system remains at rest. If I did that, I would have more variables though. I was able to, using the torque equation, I'm able to have less variables. If I solve for tension in the other one, it would be mg minus FA. So I would have had more variables. I think this answer is going to be a little bit better for us because all we need now is the mass, and we can solve for tension. We're only short mass.
Mr. Watley,
Yes.
how did you set up the net torque equation? Like where each of the variables come from?
No problem at all. Can we look up at can you see the picture that I drew on the top right corner and it has the yellow arrows coming from it?
Yes.
Okay. Now, when we're looking at the different torques, since the pivot is on the far left side, we're not going to include FA in the torque equation because it has no distance. And we know torque is force times distance, so it would be FA times 0 because it's at the pivot. That's going to tell us that, hey, that's not included. Well, what other forces do we have? MG's going down, and MG would cause the rotation to be clockwise. And then we have tension going up, and it would want it to spin, it would force it to spin or try to make it spin counterclockwise. So they're going in opposite directions. But since the system's not moving, I know my net torque is 0. So I assigned negative mg times its distance, which is 1/2 the length. And I added to it a positive tension times its distance, L. And I said that when I sum those two, I get 0 because the net torque in this is 0, it's not rotating. I have my negative mg 1/2 L plus TL equal to 0, add the negative to the other side, and then I just simplified.
Thank you.
Absolutely.
So you just turn the force times radius from the original equation into each part of those.
Correct.
Okay.
And then you don't include any force that's happening at the pivot point because it has no distance, meaning it has no torque.
Yeah.
Awesome. I'm glad we're asking questions and stepping through this slowly because it does build to your level of knowledge by not just hurrying through it and writing down what I write down. Now that we get to see, it says the thread is cut and the rod begins to fall. All right, so the thread is cut. Again, I'm going to scroll up so we can get to this, and I'm going to draw a new picture. All right, in this new picture, I've got, here's my rod, and then on the end, I still have FA over here. There's my FA, and then my MG's going down. Now my thread's cut, so I don't have it on the side. Now my FA, the torque from FA, the torque here is 0 because it's got no distance, so it's got no torque. All right, and it's asking us to find the initial angular acceleration. Okay, we remember that angular acceleration is equal to the summation of torque divided by I, correct? That should be right-ish, right? Sort of? Well, let's just say it is. And in the previous problem, I'm sorry, in A, back up in A, we said I is 1/3 ml squared. And then do we have torque? Well, we need to solve for torque, don't we? What would the torque of mg be? Can we put that? We can put that in real quick into our picture. The torque from mg would equal what? That would be mg 1/2 L, wouldn't that be? mg 1/2 length. All right, I'm not worried about the direction on this one, and I'll tell you why. I worry about if it's positive or negative, if I have torques going in different directions and I need to identify this one's positive, this one's negative, I add these together, I subtract that one. But now that I only have one, I'm not worried about making it positive or negative. I'm just going to make it positive because it's the only one I have. Remember how negatives are just directional in physics? So we can say, okay, that is the torque and it's going to go clockwise. We're fine with that. We only have to identify positive or negative if there are multiple torques that have different directions. Okay, if we're okay with that, going back to the alpha, our summation of torque divided by I, well, the only torque I have on this is mg times 1/2 L divided by the I for this problem. That comes from the very tip top, 1/3 ml squared. 1/3 ml squared. Okay, well, we can clean this up a bit, right? Let me do that in a different color so we can, it's a little bit more distinctive. Ooh, let's do red. All right, the square takes care of the L. M takes care of the M. And then the 1/3, we can put the 3 on the top, and the 1/2, we can put the 2 on the bottom. So when we clean this all up, we would have what? 3G over 2L? 3G over 2L. Okay, so far? Is the 1/2 L the force applied? 1/2 L is the distance. Remember, for torque, it's force times distance. And the question sent to me is the 1/2 L the force applied? The 1/2 L is the length that mg is from the pivot point. The pivot point's on the far left. Mg is at the halfway point along the length. Okay, perfect. All right. And I explain it that way because if I read it from one person in the chat, I'm going to assume at least a couple of other people are questioning it as well. The next part, CII, find the initial linear acceleration of the center of the rod. Find the initial linear acceleration. Well, we know linear acceleration, let's see, alpha is equal to what? A over R? Okay, and if we rearrange that, A is equal to alpha times R, right? And if alpha is 3G over 2L, and then they're asking us to do it for the center of the rod, the distance to the center of the rod would be 1/2 L, wouldn't it? And then if we simplify this or do the math, we come up with 3/4, and then the L's cancel. So 3/4 G times G. You could say 3G over 4, it's the same thing. That's the linear acceleration of the center of the rod.
Mr. Watley,
Yes.
how did you get the moment of inertia for the initial angular acceleration? So like the denominator of that, where you cross the stuff out for acceleration.
Oh, on my left, you're talking about the left margin.
Yes, the denominator.
Okay, yeah, the denominator. Remember, so here we're looking for, this goes up to B, right? Where we have alpha, which is angular rotation, is equal to summation of torque over I. If we scroll up, we solve for I right there in number 1A. We said I for this system is 1/3 ml squared.
Okay. Okay, yeah, that makes sense.
That's no problem at all. We only have one more for this example. It says find the initial linear acceleration of the end of the rod. Okay, well, we know that A is equal to alpha times radius. We said that alpha is 3G over 2L. And then for the end of the rod, that's going to be a full length away. So we're just going to multiply by L, which would give us 3/2 times G. All we're doing here is changing the radius because at the halfway point compared to the end, it's a different radius. It's further out from the pivot point. I hope that once we see CI, C double I and C triple I get a little bit easier because once you solve for alpha, then you're just multiplying by the radius in order to get the linear acceleration.
Mr. Watley,
Yes, sir.
I had a question about the inertia. So we said it was 1/3 ml squared, right?
Correct.
But what I'm confused about is like what I don't understand is where's the center point for this equation? Like, is it at the thread or is it at the force applied?
When you mean the center point, tell me more what you mean by the center point. Are you saying the center of the mass?
Because I thought force applied, wouldn't have an inertia because you said it was zero, like the length It was 0 for that.
I think he's talking about the point of rotation.
Yeah.
Okay, so the point of rotation is at the end, and I was giving it a force applied because it's like legs on a tabletop. It has a force applied, but it has no torque because there's no radius difference between where it's located and the pivot point. It's at the pivot point. So it has no torque, but there is a force there. Otherwise, the rod wouldn't stay in place. It would fall.
Pius, they gave the horizontal axis the point of rotation in the diagram, in the problem. Like it's defined there.
All right. Thank you.
Okay. All right, if you guys were able to answer that, let's take a look at what we have down here. Here, there's two things. We have a ring and a rod. We have a ring of mass M, and it's telling us that M is equal to 2 kg. So a ring of mass M, 2 kg, has a rod of the same mass placed along a diameter. The length of the rod is 1.5 meters. An axis is placed through the center of the rod, and the system is free to rotate. Okay, so you got a hula hoop and a rod going right through the middle, and the rod is the diameter. And we need to find the rotational inertia of the ring rod system. Okay, let's make a couple of notations. Going back to black. Red seems like I'm griping, so let's get rid of that. We've got a ring. What do we know about a ring? I equals what? Anybody remember? Our formula for a ring. What's I equals what?
MR squared.
Yes, mr squared. Perfect. And then what's the radius of this ring? What is the radius of this ring? It's in the given.
0.75.
Exactly right. I'm just getting all this written so it's easier to find the information. All right, then I'm going to use the other side. I'm going to just make this the rod. And this rod is rotating about the center. So what is its moment of inertia? A rod that rotates from the center. What do I equals what? Do, do.
1/3 ML squared.
No, that's from the end. This is from the center now.
1/12.
Yeah, there we go.
Someone said it in the chat first though.
Oh, it is in the chat. I'm sorry. I should look at the chat. Actually, two people answered it in the chat. I should look up at that a little bit more often. ML squared. All right, we've got 1/12 ML squared. All right, a couple of things we're just writing down, just trying to simplify it. Okay, we know that we've got a ring. We know we've got a rod. We've identified the formulas for each. We know that the radius is going to be 0.75. We know that the length of the rod is 1.5 meters. So we can say length equals 1.5 meters. Okay, blah, 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 da, 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 da. Okay, find the rotational inertia of the ring rod system. Okay, let me scroll this up to where I can just get to the answers a little bit better. The total moment of inertia, so total, would equal I of the rod plus I of the ring, which equals 1/12 ML squared plus MR squared, which equals 1/12 times, they told us M is 2, times, they told us the length is 1.5. And we have to square it. I put it in parentheses because it's being squared. I don't want you to think the whole sentence is being squared. And then we have to add to that the mass, which is 2, times 0.75 squared. When we do the math, when I calculated it, I got 1.5. kilogram meters squared. Okay, so if we're good there, let's see where the problem goes. Several turns of a string are wrapped tightly around the circumference of the loop. So this is the same problem, all right? Mass is still 2. They've already told us that. Don't feel like it's a different problem. This is B, followed up from number 2A. Several turns of a string are wrapped tightly around the circumference of the hoop or ring. The system is at rest when a cat, also of mass M, which would be 2, grabs the free end of the string and hangs vertically from it without swinging as it unwinds, causing the rod hoop assembly to rotate. Neglect friction and the mass of the string. You may need to draw a picture. I agree. Let's draw a picture. All right, so there's our ring. There's our rod. And then we've got string wrapped around. The string is coming down. And then I'm going to draw the cat as the free body diagram as a box. I can even put in here cat if it makes you feel better. Going down, they said the mass of the cat was M, right? So this would be mg going down. Yes, we've got tension pulling up, and we've got tension pulling down on the ring rod system. So the tension is pulling the ring rod system, causing it to rotate, is pulling it down. Tension is pulling up on the cat, resisting its fall from mg. So we sort of got our picture laid out, right? And if we want to just put a note in from number 2A, we said that this system's rotational inertia is equal to 1.5 kgm squared. All right, that's just our solution from the previous part of this problem. Now we can start to answer the questions without flipping back and forth, hopefully. What is the acceleration of the cat as it falls? Okay, well, acceleration is equal to the net outside force divided by the total mass. So I'm going to put MT just so we can know it's total mass, total effective mass, total mass plus total effective mass. So all the mass that's there. Okay. Now, what's the only force acting on this system? mg. mg is the only thing acting on this system. Okay. What masses do we have acting on this system? What masses do we have acting on this system? Well, we've got the mass of the cat plus the mass of the system. And I'm going to put MC and MS. You can write it any way you want to. I'm just writing it the way that I'm speaking it. The total mass, we've got the mass of the cat, and then we've got the effective mass of the system, the rotating system, right? I'm just going to step it one step further, and I'm going to say that still at the top is mg. At the bottom, we have the mass of the cat, and the mass of the system, we've always said, or starting today, is I divided by R squared. Right? When we said what an effective mass is I over R squared. Because because I equals mR squared, so effective mass then would be I over R squared. All right, let's step it one step further along. mg, what is mg in this case? Well, the cat's mass is 2 because they said mass of m, and they told us m equals 2. All right, so I'm not making that number up. I'm not calculating it. I'm taking it from number 2A. They said it was 2. We know gravity is 10. Divided by the mass of the cat. They said the mass of the cat is 2 times, mass of the cat is 2 plus I divided by R squared. Well, I, we said is 1.5 divided by r squared, which would be 0.75 squared. Now we got to math it. All right, let's see. On the top, I'm going to have 20. I can do that math. On the bottom, 1.5 divided by 0.75 squared times, no, plus 2. I get 4.67 on the bottom. 20 divided by 4.67, I get 4.28 as my acceleration of the cat as it falls. 4.28, and that'd be meters per second squared, because that's linear acceleration, meters per second squared. Wow, I think I just blew everybody's mind because everybody was willing to ask a question just went silent.
Mr. Watley,
There we go. That's what I was looking for. Yes, sir.
why would gravity be positive and not negative?
Because we can dictate we can dictate it however we want to. I can say up is positive, down's positive. For any question, we can dictate what it is. Here, if I wanted to give a final answer, I could say that 4.28 meters per second squared downward would be a complete answer. If this was a test, well, if it was an AP test, they would have to tell you gravity equals 10 and down is negative, or they would have to indicate which direction is which. But you are able to decide when you create your question, which direction is positive and which direction is negative, because the negatives are just a indication of direction. So yes, I've only told you 4.28. I should have also said down. And by saying down, that takes place of the negative.
Okay, thank you.
And if you do say negative 4.28, a complete answer would have to indicate when negative is down, or you'd have to have said somewhere that negative means downward. But yeah, legitimate question. What do we have? Yes, what's up?
So I see in like the first step, you say mg over mc plus ms. I'm assuming ms is the massive system, right?
Yes, the mass of the rotating system.
Okay, so then why don't we just say 2 plus 2, because like both have a mass of m, right?
But it's not their actual mass like you put it on a scale for the rotating system. It's their effective mass. It's their inertia, which is their resistance to rotate.
Okay.
Yeah, so that's why we call it the effective mass. It's the mass in the way that it affects the system. And when we're looking at its mass, we're really looking at its inertia, which is its resistance to rotate. And how do we handle it? It's its resistance to rotate was that a 1.5 kilogram meter square.
Okay, thank you.
Divided by the radius squared, yes. Okay, what is the angular acceleration of the ring rod system? What is the angular acceleration of the ring rod system? We know angular acceleration is equal to A divided by R. And then here we would have, what would I say the answer was? 4.28, all right, 4.28 divided by 0.75. All right, so let me put that in my calculator, 4.28 divided by 0.75. Here I get 5.71. And this would be radians per second squared. This last one is, what is the tension in the string? The tension in the string. Okay, for this, I'm going to look singularly at the cat, because I know I've got tension going up and I've got mg going down. I know that the acceleration is in the downward direction. My summation of forces is equal to mg, and I always take the direction I'm going and subtract. I take my bigger force and subtract my smaller force. So mg minus t is equal to mass times acceleration. If I rearrange this, I would get what? T is equal to mg minus ma. So then T is equal to 2 times 10 minus 2 times, what do we get for 4.28? Okay, so then tension would equal to 4.28 times 2. 20 minus that, 20 minus that, 11.44. That funky thing right there is supposed to be newtons. So the summation of forces, the difference in forces is equal to mass times acceleration. Here I'm still keeping downward as positive. That way I can use a positive 10 and I used a positive 4.28. If you want to make downward always negative, then you would have to make the 10 a negative and the 4.28 a negative as well. It would just change the signs, that's all. Here I'm just looking at the magnitude, but the magnitude of tension would be 11.44. I think the next problem is doable based on what we've talked about in our notes. So as long as you have the notes, you can get through number 3. That gets you to the bottom of the page, which will then finish this all together. And then you'll go to this torque, acceleration, velocity, practice problems. That's part is for homework. So finish up number 3. Let me know if you have questions. And then for homework going into next class will be that last page. Those are the things that I want you to work on between now and next class.